In the last episode, we saw how 2030 marked humanity's shift from lunar visitors to tenants. NASA and China built outposts. Year 2033. This is the Aurora Collaborative Lunar Mission, a joint effort by ESA, JAXA, and private partners, launching small-scale robotic and crew-assisted visits to the Moon in 2033. How will these missions prepare us for longer stays? What tools and habitats will we test on the lunar surface? Which science and business goals drive this teamwork? And how will humans and robots work side by side? And most importantly, how will these early trips shape our future on the Moon? The story starts at Europe's Guiana Space Center. Here stands the Vega XL-3 rocket, carrying the Aurora cargo lander. Inside, there are drilling tools, solar panels, and a six-wheeled rover called Helios Scout. The countdown hits 0, the engines roar, and after a few minutes, Vega XL-3 puts ACL into low Earth orbit. 2 days earlier, a Japanese H-3 rocket launched the Aurora Crew Transfer Module, ACTM, with 3 astronauts and extra robotics gear. Once in orbit, ACL and the crew module meet and dock. Together, they fire their engines for a precise trans-lunar injection burn. Under watchful eyes in Darmstadt, Toulouse, and Tsukuba mission centers, the spacecraft speeds up to 11 kilometers per second and heads toward the Moon. Over the next 3 days, the astronauts check life support, set up Helios Scout's cameras, and practice landing drills. Meanwhile, ACL separates and coasts into a special near-rectilinear halo orbit around the Moon. It carries seismic sensors and drills for sampling regolith. On day 5, the crew vehicle performs a lunar orbit insertion burn. It slows from 2.3 kilometers per second to about 100 meters per second, settling into a polar orbit that passes above Shackleton Crater near the South Pole. This crater is in permanent shadow and holds water ice. With a one-way delay of just 1.3 seconds, every command must be timed perfectly and backup plans programmed in advance. Day 7 brings the first robotic landing. ACL fires its braking thrusters for nearly 4 minutes, slowing down above Shackleton's rim. At 100 meters altitude, it uses a hover and slam move to touch down, kicking up a cloud of lunar dust. Once clear, ACL unfolds its solar panels and begins drilling into the icy soil. It pulls out cores to check water content and quality crucial data for turning ice into water, oxygen, and fuel. Next, Helios Scout detaches and lowers itself with cables like a small sky crane. On the ground, the rover extends its robotic arm with a laser spectrometer and ground-penetrating radar. It scans the area to map ice layers and find mineral deposits. Over 2 weeks, rover and lander share data proving that we can mine ice on the Moon. In orbit, the ACTM gets ready for descent. On day 14, the 3 astronauts strap into the crew descent vehicle CDV. They watch monitors as the CDV separates, does a deorbit burn, and starts a controlled retropropulsion sequence. Its sensors pick a clear landing spot 500 meters from ACL to avoid dust interference. Under gentle deceleration, the CDV soft lands at Shackleton's rim. The hatch opens, and astronauts step onto the lunar soil in their flexible Generation 6 EVA suits. These suits have cooling loops and allow up to 8 hours outside the vehicle. The crew inspects ACL and Helios Scout, then attaches new test items, a small inflatable habitat mock-up, an ISRU unit that heats regolith for oxygen, and a deployable communications relay. All the while, Earth-based teams watch via HD cameras to see how well humans and robots work together. For the next 10 days, each day follows the same routine. At the start of each lunar day, which we call Coordinated Moon Time (CMT), the crew does health checks inside the CDV's sleeping area. Then they suit up for a 90-minute maintenance session, greasing rover wheels, fixing minor software bugs, and mounting a panoramic camera on ACL. At midday, they return to the CDV to recharge tools and share updated data with mission control. Science goals drive every minute. The crew drills shallow regolith cores to test grain size for 3D printing building blocks. They run the ISRU reactor prototype, feeding it 5 kilograms of regolith per hour to make 2 liters of oxygen. They record moonquakes with ACL seismometer to find lava tubes, natural caves that could protect future habitats. They tag patches of ilmenite, a mineral that could help us make steel on the moon. Communication is tricky. Shackleton's rim sometimes blocks direct signals to Earth, so data routes through the Lunar Gateway Relay. A 10 megabit image or a 2 kilobyte status update takes under a minute to reach mission control, but commands back to the crew see a 5-second delay. Quick actions like steering Helios Scout down a steep crater wall happen autonomously. The crew acts as supervisors, ready to step in if needed. On day 23, the crew tests the inflatable habitat. They unfold the 10 by 6 meter module, anchor it with 8 harpoon stakes, and inflate it to 1 bar pressure. In 2 hours, the module stands ready, its walls lined with reflective foil and sealed against dust. Though meant as a short test, this habitat shows how future lunar bases might work, giving data on temperature control, dust resistance, and interior layout in 0.16 G. As the mission nears its end, the crew prepares to leave. They pack 120 kilograms of precious samples, ice cores, soil bags, and rock pieces into a return capsule. They seal the hatch, jettison the habitat mock-up, and climb into the CDV for ascent. Its engines fire, lifting the vehicle from the surface and pushing it toward lunar orbit for a rendezvous with ACTM. Helios Scout powers down into hibernation for recovery by later missions. Day 27 brings a smooth docking in a 100 by 100 kilometer orbit. The CDV hands over its samples to the Aurora Sample Return Container, ASRC. The crew then fires the trans-Earth injection, burn a 3-minute, 1.8 kilometers per second maneuver that sends them home. Back on Earth, ships and helicopters wait in the Pacific. Splashdown is planned off French Polynesia, where ESA teams will retrieve the ASRC and rush it to labs. The Aurora Collaborative Lunar Mission wraps up with clear wins. Over 200 kilograms of samples returned, the first crew-assisted robotics trial at the Lunar South Pole, and key data on small-scale ISRU, habitat setup, and crew autonomy. Less than a month after launch, the astronauts returned to cheers in Kourou, Toulouse, and Tsukuba. Their success in 2033 lights the way for the first modular base segments, permanent living habitats, and full-scale resource operations, stepping stones toward a lasting human presence on the moon. In the next episode, we see how Mars receives its first return rocket for samples and a rover to prepare for first human mission in 2038.